Okay, I think I'm recording now. For some reason, it wasn't shut. All right, I'll share my screen. All right, I think it's all good. And we're recording. Okay, sorry, just a couple of minute delay then. Some technical difficulties this morning. So welcome to session 3, and today we'll talk about measuring Haversian canals and tracing secondary osteon cement lines, which essentially also means measuring them, basically. For those of you who are new to the session today, I just want you to think that, or imagine that you're here in the lab at the Australian National University, and you're sitting by a microscope, and we're just taking a look at some examples of bone histology on the big screen, and we're figuring out how to quantify the data that we see on the screen. And we've already covered some basic things the past couple of sessions, and today we're going to be also still looking at secondary osteons and their concentric lamellae. I told you osteons will become your very good friend. But in addition to just secondary osteons themselves, we're also going to be looking at Haversian canals. So Haversian canals are basically just the central canals that run through the center of an osteon. And each Haversian canal contains blood vessels, some lymphatic vessels, as well as nerves. So as you can imagine, a Haversian canal is actually quite an important component of a secondary osteon, because it basically facilitates blood supply and exchange of oxygen and very important nutrients that basically keep your bone alive. So the very important aspects, or basically structures that we'd like to measure. And just by looking at this very simple diagram, you can already tell that there's quite a lot of variation in the size of these secondary osteons. And so that is indeed what we're going to be talking about today in this very brief session. So from last week, we talked about densities, and today we're going to move on to geometric properties of secondary osteons and their canals. The basic principle that you just need to take out from today is that it's a simple geometric measure of a biological structure, just as if you had a simple circle and you were interested in its circumference, except that we typically don't really look for circumference or perimeter. We technically look at the entire area, so we would report it in microns squared, or things like diameter. If you want to know about the width of that surface of the secondary osteon, we wouldn't really look at the radius, just clarifying. And in the literature, what you find are a series of abbreviations. I introduced last week intact and fragmentary osteon densities, but for the geometric properties, you could see things like H.AR, which stands for Haversian canal area, or ON.AR, which is the osteon area, or diameter. So these abbreviations is basically what we use to code these the measures of secondary osteons. In fact, it's right now, as we're halfway through the series, it's really important to point you to a very important document that we use, or paper, obviously, that we use in bone histology. This is a paper that was published in 2012, led by David Dempster in Journal of Bone and Mineral Research, that basically talks about standardized nomenclature, symbols, and units that we use in reporting bone histology. So it's very important to report your data and describe the variables using the common language, right, that scientists can refer to no matter what lab you're from. Now, at this stage, I should also point out that when we're talking about geometric properties of secondary osteons, there's more that you can measure. It's not just the diameter and the area. You can look at circularity values. There's several things you could do, or things like aspect ratios or inverse of the aspect ratio. Obviously, this is a very introductory session, so please feel free to go away and look into it a bit more and play around with your samples. Yeah, the world is your oyster, right? So obviously we have to go through a bit of the biological background and link the whole the data to what information they can actually give us. Now, so as a reminder, last week we talked about the bone multicellular unit, so that cutting cone that's that's digging tunnels in your cortical bone. And you remember that it looks something like this. So it's sort of an elongated 3D structure that's digging through the cortical bone, and it's lined with bone resorbing osteoclast cells. And you remember we talked about how if you take a cross section through such an osteon, basically what you then see in the thin section could be any of these stages. So you could have like a resorption bay that is basically just a large hole in the bone, which is a result of these osteoclasts basically paving the way for the remainder of the osteon. But if you're looking at a completed osteon, it will look something like this. So it's a circular structure with a Haversian canal in the middle. Now, we talked about densities and the formation rate, I suppose, of these structures. But what we can also, I guess, collect is the information about how much of that bone itself there is within that osteon. So those lamellar structures, that are formed within the osteon itself, they're basically an indication of how much bone matrix there is within one single unit. And as you can imagine, there'll be quite a lot of variation even in one localized area in the bone due to several different reasons. So we can measure that basically by quantifying these geometric properties. So technically speaking, I guess quite basically, those measures such as HR, the diameter and the area of the osteon, we technically take them as an indicator of the refilling activity of that bone multicellular unit. So you could imagine that larger osteons are basically possibly having more bone than smaller osteons. So it's already giving you an insight into that activity of remodeling in the section. Now, last week we talked mainly about primary osteon. That was week 1 actually, when we talked about aging. So we had a primary osteon, and we also talked about what I call a typical osteon. So here's just an image taken from a book chapter that Sam Stout with colleagues published recently. It's excellent. The reference is at the end of the slides, so you can follow that up if you're interested. So here's just looking at this picture. So here's a tiny little primary osteon. We sort of already talked about this. And then C is a typical osteon. So here we've got, one here, there's another one there. So this is the sort of thing we covered last week. Now, what I didn't tell you is that a typical osteon, such as that one coded as C, is what we call a type 1. So type 1 is the most commonly occurring secondary osteon, but we can also have type 2s. Type 2 are essentially embedded osteons. Now, here we're actually looking, for example, at this one, E or D. So what that means is that you have another secondary osteon that is basically remodeling within a pre-existing osteon. So that's a very interesting phenomenon because it basically tells you that this osteon that's within this other osteon is a later remodeling event that's occurring in the same site. They're typically quite easy to tell from the thin section. Obviously, it takes some experience and time, I suppose, to differentiate what's what. But the idea is that you actually have 2 separate cement lines, and we'll get onto cement lines in a minute. And B is just a resorption bay, which we mentioned last week as well. But yeah, just want to show this as a reflection of, how that BMU activity, what it can basically turn out, or what products it can leave behind in a thin section. So type 1 and type 2. Type 2 is embedded. Now, that's not all there. Unfortunately, it isn't over. There's just a couple more types of osteons that you could see in your thin section. So here, I think I have to move this up so you can see. Hang on. I'll just move this. What we've got here is that type 2 that I just mentioned. So you can see that there's one osteon here, another the pre-existing, and then the pre-existing osteon sort of underneath. And we've got 2 cement lines. Now, I told you this is later remodeling event, but what you can also see is something really bizarre that looks like that, which is what we would call a drifting osteon. And so the surface is here, but you actually also see a tail that's sort of, running sideways. And so this is an example of a secondary osteon that for some reason, and we still really don't fully understand what that reason is, papers have looked into various different possibilities, biomechanics, malnutrition, possibly even genetic predisposition, but we still don't really fully understand what it is, or what causes the drifting osteons, I should say. I suspect it's just natural variation, because as we'll talk about this a little bit later today as well. Remember, the BMUs are 3D structures, right? And so they sort of branch and cluster, they branch out naturally. So I think it's just possible for it to lose its course. So anyway, if you see something like this, like a long tail, it's what we call a drifting osteon. And then the only other one that we still need to probably bring up for you to take away from this session is a double zonal osteon. Now, this one is, it looks a little bit similar to a type 2, because it does look as if it's embedded, the smaller one is embedded in a bigger one. But the difference actually is that there is basically no cement line, or what we call that reversal line, of a BMU. But what we do see is just a simple boundary that is an arrest line. So this is an example of an osteon that was forming, but something happened, possibly physiological, that arrested that growth a little bit. And then so that osteon stopped forming for a while, and then it basically continued forming again. Now, those of you who are into physiological stress, you're probably already thinking that this is a great indicator for looking into evidence for some form of stress that impacted an individual. As far as I know, very, very few people have looked into that. And some people have asked me previously whether a double zonal osteon is possibly similar to like a line of arrested growth that you would see, in other animals. Or even possibly, could this be an equivalent of something like a Harris line, in the trabecular bone? Now, the answer is we don't really know. So I'll just leave it at that in case you're interested in that question. Okay, so before we move on, I wondered whether I could ask you to, could I ask you to tell me, I'm trying to move this again. Sorry, let me just, not sure. Oh, there we go. Could I ask you to tell me what this osteon here is in this picture? Does anyone remember? So remember, you've got just the surface here and then a tail that's running. What would you call it? I'm just going to check your, excellent, fantastic. Excellent, so that's a drifting osteon. So if you see these in your sections, you've got drifting osteons. Thank you. All right, and then the next slide. There we go. Now, would you be able to tell me which one is a type 2 and which one is a double zonal osteon in this picture, bearing in mind what I just kind of talked about? So left, this is just the left and this is right. Would you be able to tell me which one is double zonal? Okay, so we've got actually a mix of, oh no, overall most people, left double. Okay, bear with me 1 second. I'm just going to check it out. Okay, so there's a mix of replies. Most people seem to be on the same page. So so the left one here is a type 2. So it has 2 separate cement lines. So this is an older osteon here, and this is a younger osteon. And the 2 separate remodeling events, but contained within 1 unit. And then this one on the right is a double zonal. Now, this picture is actually not a thin section. It's a scanning electron microscope image of a bone surface. Now, the reason we would call this a double zonal is simply because you only see a very fine kind of periphery sort of line here, but it's not actually a cement line, and there are no very distinct lamellae forming on the inside. So you just know that this osteon started forming, and then that formation got interrupted, and then the osteon continued then forming again. But yeah, good job overall. All right. Sorry, moving on. Okay. So yeah, so this is just kind of an overview of the different osteon structures and how they relate to BMU formation. And so when we're talking about quantifying these geometric properties, we typically trace osteon cement lines and the border of the Haversian canal. Now, I've mentioned it several times now. I keep using the term cement line. It's basically a reversal line of the BMU, and we also still don't fully understand I guess, the composition of it and what it actually is. I very interestingly spoke to a bone histologist at a conference last year, and who basically was convinced that they're not a real thing, and he thinks that just it's just basically sort of like a shadowing effect or an optical effect that you see in a thin section simply from neighboring cement lines. You know, I can't comment on that, but obviously according to the literature and from the stuff that I've seen in my samples, we think that they're possibly just very highly mineralized, or alternatively, I guess you could call it just collagen deficient reversal lines. But the idea is that we trace them to find out how big the osteon is. And why would you want to do it? Well, my biggest interest, and I guess according to the literature, why people mostly study these geometric properties of osteons and the Haversian canals, is mainly looking at adaptation to load, so localized biomechanical remodeling. In fact, Van Ers and colleagues in 2008 published what we now refer to as one of the most important papers in the geometric properties of secondary bone, called Relating Osteon Diameter to Strain. And they actually did a mathematical modeling showing that we can predict the size and the shape of osteons according to mechanical strain. And here's a very good example from the paper showing you, for example, different biomechanical load and strain sites of one bone. So they've observed that endosteal endosteal sites that experience mainly tension, they actually tend to produce larger and sort of wider secondary osteons compared to sites that mainly show compression. And this is from one individual, and you can already tell that the huge difference in these in the structures, in the size of the structures. Now, this is actually from an elk, so yes, just pointing that out. And again, I mentioned, I think last week, please, I would definitely encourage you to read some of the work by John Skedros, because this is the sort of work that he's into. We'll revisit him a little bit more when we talk about collagen fiber orientation in week 5. So I guess for, those of you listening today, if you're in archaeology and forensics, if you have a fragment of bone and you're kind of trying to figure out maybe which part of the bone it's from, or you're comparing a series of individuals who show possibly different indicators of physical activity, it's certainly, histology is certainly a technique you may want to consider to figure out the data. And shout out to Bonnie. I'm not sure if Bonnie's logged on today. Bonnie is an ex-student of mine now. She did a little project in my lab a couple of years ago, and she actually looked at osteon area in archaeological individuals. And I just wanted to show you an example from her research project. Here are some insane, basically very good examples of the variation that you get to see even in one location. You know, these osteons go from really small to really big. And in fact, Bonnie and I called it, you know, this one in particular, the giant osteon. And she looked at different anatomical sites as well. So just wanted to give you an example. What you're probably also noticing is that this giant osteon is very white compared to some of these other darker ones. We will revisit this in week 5. We're going to be talking about collagen fiber orientation, so stay tuned. The other reason why you may be interested in this are bone metabolic issues. We talked about this last week as well. You know, osteoporotic bone, excuse me, osteoporotic bone will have these huge resorption bays everywhere, and the majority of the secondary osteons will have very large Haversian canals that are possibly still indicating secondary structures that are forming and basically resorbing bone compared to something that's a little bit healthier. So if you're able to quantify that, then you can start arguing that a bone was possibly compromised. And last but not least, most importantly, it's the actual vasculature of bone. Now, I asked you just in preparation for today to have a quick look at a 3D render of a Haversian kind of vascularity system in human bone. And if you did have a look, it's, you know, one of the really beautiful aspects of microscopy that we can actually do this and look inside your bone tissue. But it's an incredibly complex structure, and for you to be able to figure out the size of these blood vessels and how they're connecting will give you very interesting information about how well or poorly vascularized a bone sample is. Okay, so what we're going to do now is just do some measuring. So I'll just show you a couple of very basic tools that we do, and feel free to, I mean, I'm not sure if you've got two screens, it probably works for you. I know most people probably don't, but you can basically follow what I'm doing and do it yourself, or yeah, again, do it later in your own time. It probably works easier. But we're going to just to follow the same procedure we did last week. So we're importing image into ImageJ, setting the scale, measuring the variables, and then calculating averages. So I am now going to stop share. And I'm just going to share my screen, which I hope you can see. I just need to minimize this. Sorry, bear with me one sec. All right, so we've got ImageJ up. Most of you probably know it quite well by now, hopefully. And then let's just do the OPD practice sample from my website. Now, remember what we've got to set the scale. So I'm just going to zoom into the picture. Sorry, let me just do that. So we're going to set it to, and today we're going to set it to microns. We typically analyze set scale. So last week we were working in millimeters because we needed to figure out the area of the sample, the image that we're working with. But for the purposes of geometric properties of secondary osteons, we typically report in microns, or microns squared for area, and then microns for diameter. Whoops, microns. I may set it to global because I think the other one's the same. All right, so zoom out. Obviously, it'll be important to have very good quality images. These are not the best, but we're sort of trying to do a more introductory thing, and I'm using the same sample for several different variables. But for the area itself, for Haversian canals and osteon area, you can really do two things. And in the literature, people who do report the use of ImageJ, they report two different tools. So some labs use the freehand selection, and some labs use the polygon selection. For me and my students, it really is a matter of preference. I personally prefer the polygon selection, and I'll demonstrate in a second why. If you're working with the freehand selection, ideally you'll have one of those, styloid pens that you can use on like an interactive screen. Some people do it on a tablet, or on an iPad, so that you can actually manually trace the border or the cement line. So for that reason, the polygon selection is actually a bit easier, personally anyway. So if we, I don't know, let's just pick this one. So, okay, zoom in to the point where you're quite confident just tracing around the osteon. What you'll find is these black dots are actually osteocyte lacunae, which we'll talk about next week. What you find, if you don't see a very distinct cement line, is that these black osteocyte lacunae actually arrange around the periphery of the osteon. So if you take a look at this one here or that one, you can see that they're more horizontal. So that's already indicating that the bone around here no longer belongs to that one secondary osteon. So if I was to trace it with the freehand selection, so I'm just doing it with the mouse. So obviously this is not going to be perfect. I'm just demonstrating, but I'm just going to go around as I guess as well as I can. Now, remember, this can obviously introduce some intra and inter-observer error. So it's important that you typically measure this at least 3 times and then possibly report an average. And then if you've got a bigger team that you're working with, ideally you will also do an inter-observer test. So do your own measurements, get someone else to then measure them for you and compare your data to make sure that you're taking these measurements consistently. Now, once you've traced this, once you've drawn a line, you can press D on your keyboard, and it stands for drawing, for draw, and that will basically burn that that line into the picture itself, so that you know what you've already measured and what you haven't measured yet, and then press M for measurement. And so we're getting approximately 44,057,785, which is actually about average for secondary osteons. And so you just continue doing that, right? So I don't know, let's just do that one. But what I will do this time, however, instead of doing using the freehand selection, because as I pointed out, it relies on you being able to trace carefully. And if you have a shaking hand, it's not going to work. Now, the polygon selection helps you actually do it in little bits. So click and you start going round. It's really entirely up to you, you know, how big these little segments are. But it helps you also readjust it. So if I just go around, this looks like it's still a part of that. So we'll do this. You join it there, and then remember to again click D for drawing. You do that, and then take your measurement. So back to our measurements, and this one's much smaller, so it's 15,883. And yeah, so you just continue doing that for all the osteons that you want to measure. Now, the only other thing maybe I should demonstrate is how you can also adjust it. So when you click on these little white dots, you can actually move your line a bit and readjust it if you feel like you didn't select it properly or, you know, accurately in one region or another. So in your image J pad, in the data, what you've got is the actual area. So these are the data that you want. For today, I'm just going to leave this window up, but I'm going to take this one out, and then I'll just put in the polarized light image. Now I think I've already set it to global. Yeah, that's fine. Now for the Haversian canal area, I would typically work with polarized images like this one because they bring out the Haversian canal borders a little bit better than the transmitted light only. So let's just do this one. Again, I'll be zooming in as much as possible, and ideally you really want to be able to see the pixels. So if you zoom into the pixel level, you know that you're basically very close to yeah, you know, to the quality of that. So if we just use the polygon selection again and just go around the border. Sorry, again, I'm demonstrating, so I know this is not probably ideal. If you, obviously the better quality the image, the better, because it means you can actually have a really nice quality, very good quality data. I think I'll just do these, draw, measure. And in our data, we're getting 2,027. So that's also actually pretty average. Most of the samples I've ever worked with are typically just over 2,000. I don't know, let's just do one more. I mean, you get the gist, right? So if maybe let's do this one looks pretty good. And let's try and do this one with the freehand selection. So I'll just do that. And so if you are patient enough and you want to do this for ages and you have lots of samples, then you should become a histologist. Okay, this one's about 2265, and yeah, and we just keep going. Now, the only other thing we should probably mention is also the diameter. So perhaps we should swap the picture again. So I'll just do that and pop that one back in. For the diameter, what you really just want is a straight line. So just click on the straight line tool here, which is what we use for setting the scale. And if you have a lot of osteons that perhaps are a bit more elongated, or you know they're not as circular, you may want to report, let's say, the maximum and the minimum diameter. So you can just basically, you can simply, you know, figure out, ideally you'll go through the center of the Haversian canal as well, what the maximum diameter is, and then what the minimum diameter is. So I've just done that and pressed M. And so here's my data. And so like I was saying, you know, if you continue doing this for several osteon structures and several images, you'll start building up a big data set. Those of you who are not aware, you can actually save the image J output as an Excel spreadsheet. So you just click File, Save As, and sorry, Save, yep, on your desktop. And then it basically becomes your raw data. I just said data. I'm picking this up from in Australia. Yeah, there we go. Okay, we're slowly approaching the end of the session. I know it's already 8:32 on your watch or our clocks, but we were a little bit later today. According to my phone, it's still 3 minutes. So that's that. I will stop sharing this, and then I'll share my PowerPoint again. Yeah, there we go. So if you've taken all of your data from one image, you may want to calculate an average and then provide that in the paper. And what I just want to mention before I let you all go is that it's very important that you think about bone histology from a three-dimensional perspective. So obviously thin sectioning is gold standard in clinical practice and, you know, in various, I guess, other biological research and medical areas, because it helps us with diagnosis. It helps us, you know, to access cell structures and visualizing microstructures generally. But when we're talking about the vasculature of bone, remember that it is a 3D feature. So what's becoming increasingly clear in biological anthropology, especially when we're trying to make some inferences about bone remodeling, is that wherever we end up taking, you know, the thin section from, it's actually not representative entirely of the bone chunk that you know, yeah, that we're studying. So ideally, which involves you know, it means you have to spend a bit more time doing it, but ideally you'd be taking serial sections, so you can take, you know, like one up here, one here, one here, or, you know, use a micro CT, pop your samples in a micro CT, which you know, in terms of infrastructure, obviously is not always possible. But here's just a picture from a paper by Isabel Maggiano and colleagues in 2016 in the Journal of Anatomy. I really encourage you to take a look at that. But it really demonstrated to everyone that depending where you section, you see this variation in size and, you know, not just the osteon itself, but also obviously the Haversian canals as well. So it's definitely something to bear in mind. And so that's why it's also really important to also be consistent in your sampling locations. That's typically what we would emphasize. But on that note, I'll leave you with that. And if you have any questions, the chat will be saved. I'll do the typical, I'll post my answers on the website. Next week, we'll take a look at osteocyte lacunae and how they relate to bone remodeling, and yeah, how we could quantify the densities and also measure them. And here are some references for you. And apologies for the slight delay today, a couple of technical difficulties at the start, possibly linked to me returning to the ANU campus. And that's about it, folks. And I'll see you next week. Bye.